Okay, let's discuss this particular paper. Let's look at question number 1. Titration can be used to determine the concentration of dissolved oxygen in samples of river water. The procedure for the experiment is given. Step 1, use 5 50 centimeter cube of graduated syringes A, B, C, D, and E to collect 5 separate 30 centimeter cube of the river water. So 50 to contain 30, it's okay. In the laboratory, carefully add 5 centimeter cube of the manganese sulfate into syringe A and mix well. And then add 5 centimeter cube of alkaline aqueous potassium iodide into syringe A and mix well. And then step 4, you add 10 centimeter cube of the dilute sulfuric acid into the syringe A and also mix well. And then you transfer the contents of syringe A into a 150 centimeter cube of conical flask. Rinse syringe A using 10 centimeter cube of distilled water and add the washings to the conical flask. So this step is to ensure that you completely transfer all the content of the syringe A reaction mixture into your conical flask. So currently now, if you look at all the volume that I circle, 30 plus 5 plus 5 plus 10 plus 10, in total, we have a 60 centimeter cube of the solution in the conical flask. And this is from syringe a total of 60 centimeter cube. All right, and then carry out one accurate titration of all the contents in the conical flask with the 0.002 mole per dm cube of aqueous sodium thiosulfate. So this is the burette, okay? And in this burette is sodium thiosulfate. And you want to titrate. And you gotta use a starch indicator. Now, if you ask me by until this step, right, sodium thiosulfate is to detect iodine. Okay, it's used to detect iodine. So, what I can think here is that in this reaction, iodine is being formed as the product. Okay, so iodine is brown in color. So when you have the iodine form, the reaction will become brown. So maybe I should use a brown color to color the conical flask here. I speculate lah. This part is iodine. Now sodium thiosulfate will react. So when the titration occurs, the brown color will fade over time. And then when it starts to fade until a pale yellow color, which normally I will tell you all in the lab where you see around pale yellow color. Pale yellow means the concentration of iodine is low already. Okay, that's the time you should add your starch indicator, like a few drops. So your starch indicator is actually white in color. So I need you to add a few drops in immediately. Iodine and starch will turn blue-black. So you're going to see the whole thing blue-black. Okay, so this blue-black is formed from the reaction of the very, very little iodine remaining and the starch. So starch and very little iodine remaining will give you blue-black. So you will titrate until the blue-black disappear. When you do not have any more iodine to bind with the starch, all right, it is because the iodine went and further react with the sodium thiosulfate, then I think the blue-black will disappear. So I think your endpoint would be blue-black to colorless. That's what I think for now. Okay. Now, we repeat step 2 to step 6 for the samples in syringes B to E. Okay. So, pare, aqueous sodium thiosulfate can be prepared using the hydrated sodium thiosulfate crystal. Determine the mass in gram of the crystal required to prepare 570 cube of the 0.002 mole per dm cube of sodium thiosulfate. So first we calculate the number of moles. So moles equals to MB over 1000. So volume 500, concentration 0.002 divided by 1000. So you get the number of moles here, which is 0.001. So mole equals to mass divided by molar mass. I calculate everything in this. So my mass is around 0.248. I will normally answer 3 to 4 significant figures around there. Normally I go 3. Now, part 2. Identify the piece of apparatus that should be used to prepare the 500 centimeter cube of the sodium thiosulfate solution after the required mass has been weighed out. So the volumetric flask is the apparatus that should be used to prepare any solution you want. And the capacity of the volumetric flask should follow the volume that you want to prepare. So when I bracket over here 500, that means the marking scheme also bracketed. It means that it is not mandatory to earn that 1 mark. So long we see volumetric flask, we give you the 1 mark. Part B, the graduation of each syringe are every 1.0. So what does this mean? It means that if let's say this is the syringe, so let's put this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A long one. Okay, so this is 5 lah. Okay, so that is called graduation of 1. So calculate the percentage error in the measurement of 5 centimeter cube of alkaline aqueous potassium iodide by the syringe. Now, the formula for percentage error is error times the number of times you read it divided by your reading of your volume. So the error made is actually 0.5. It's because you either read this as if your meniscus, lower meniscus is actually at the blue color point, which is in between the graduation. This is called 0.5. Or you could read it in between the next one, which is 1.5. Okay, so the error made is plus minus 0.5, which is, this is a negative 0.5 error, and this is a positive 0.5 error from your 1. Because the first line here, the red one, is actually 1.0. So you either read it as 0.5 or you either read it as a 1.5. So the error made is plus minus 0.5. And because when you took initial and final reading of the syringe, you made the error 2 times, therefore the error will be 20%. Next part. Place 1 tick in each row in table 1.1 to show the effect, if any, of using a larger volume of alkaline aqueous potassium iodide. So let's look at the Y, the column. What is uncertainty of the measurement? Uncertainty of the measurement is basically the error of the apparatus used. So the syringe has an error of plus minus 0.5. So whether you use a large volume or a smaller volume, the uncertainty of the syringe is still going to be at 0.5, which is why it's no effect. However, the percentage error of the measurement will be smaller because when your percentage error is defined as error divided by your reading, okay, times the number of times you read it times 100%. Now you use a larger volume. A larger volume means your reading is larger. So mathematically, if you have a larger reading, your percentage error will be smaller. So 2 ticks is 1 mark. Part C. The sample in a conical flask and the prepared solution of the sodium thiosulfate are provided. Okay, so they provided us. Describe the following procedures for the experiment using syringe A. So describe part 1. We got to describe how to prepare the clean burette before taking any readings. Okay, so how do we prepare a burette? We got to rinse the burette with distilled water. Then we got to rinse it by the sodium thiosulfate. And then we got to fill with sodium thiosulfate. So you need to make sure that you rinse the burette with the solution first. Then take it out and then you fully fill it with sodium thiosulfate. So 1 mark there. The second mark is you got to place sodium thiosulfate, which is this part of mine. This is this one. But because of the word and, okay, that's why I didn't get my second mark. And then run some solution out. What this means is when you look at your burette, you have the locker here, right? Then this part, okay, you have the tip here. Now, a lot of times when you all fill the burette here, this part is where you all completely fill the solution, here a bit. But when it comes to the bottom part, right, a lot of times I will ask you to check whether do you have some bubbles inside it. So run some solution out is to ensure that even the bottom part here is fully filled with the sodium thiosulfate. So you got to run some solution out before you even take any reading. In other words, run some solution out to excrete all the air bubbles before you even take or do your titration. Part 2, can you describe carrying out one accurate titration in step 6? So you just tell examiner how do you carry out one accurate titration. Accurate, not rough, accurate. So I answered titrate the conical flask with sodium thiosulfate from the burette. until the color in the conical flask turns pure yellow, which is where the iodine concentration will decrease, because when you titrate, iodine will decrease. So from brown color, it will turn orange, then it will turn pure yellow. Okay. Now then when it reach pure yellow, we add starch into the conical flask. Therefore, blue-black will be seen. Continue to titrate until the blue-black disappear by dropwise. So when you are almost reaching your endpoint, you must do dropwise. Okay, so if we look at the marking scheme, titrate with sodium thiosulfate is 1 mark. Okay, now mark 2, we want to see things like until the color change, all right, or endpoint reach, okay, and dropwise to ensure endpoint is accurate. So if you look at the marking scheme over here, add sodium thiosulfate into conical flask until a color change is seen or until endpoint. My answer is more detailed is because I describe exactly the color changes that occur. But over here, I think they're a little bit more lenient. They allow student to write color change or endpoint reach, just in case some of you don't know what's going on. Okay, so then the second mark is add drop whites, okay, approaching endpoint. All the things in the bracket is not mandatory to get the mark, but whatever that is not inside the bracket is needed to obtain that 1 mark. Okay. Now, suggest why the reaction mixture is mixed well in step 2 to step 4. I realize they repeat, add this and then mix well and then add another thing and then you mix well, right? So the answer is to ensure the reaction is complete. Yeah. So I wrote there to ensure the redox reaction between the reagent can occur and that the dissolved oxygen can be reacted. For me, I don't think I'll get the marks, even though I said to ensure the redox reaction occur. But I did not say completely occur, because the only thing I think of is there was a redox reaction, because the fact that iodide became iodine is a form of redox already. Okay, so that's why I wrote very detailed, like to ensure that the redox can occur, okay, by collision theory. That's why we mix well. But I didn't say for completion, so I don't think I will get the marks. Okay. Now E. Draw a table for recording the titration result for the 5 samples in syringe A to E. So I think it's quite straightforward. The initial burette reading, unit, final burette reading, unit, volume of sodium thiosulfate added, unit, and for A, B, C, D, E. So if we look over here, yeah, this one. All right, A, B, C, D, E. So M1, heading and units correct for the table. Initial reading, final reading, title of volume of sodium thiosulfate used. Then what kind of volume are you using? Because there's so many solutions that are being used in this experiment. So you got to address sodium thiosulfate, used or added. Unit must be there. Now, mark 2, 5 columns for syringes A to E. Okay. F, the overall reaction taking place in the experiment is shown. So oxygen, so this is the dissolved oxygen from the river water. Okay. And then the thiosulfate and acid. Okay, I think they add sulfuric acid, right? Something around them. Okay, so a student carried out the experiment and determines the mean titer to be 12.65. So your sodium thiosulfate is this part in the burette. So the mean titer is over here, 12.65. Calculate the concentration of the dissolved oxygen in mole per dm cube. So first, I calculate the moles of sodium thiosulfate, which is 12.65 times 0.02. I get 2.53 times 10 to the negative 5. So based on the stoichiometry, we have 1 oxygen to 4 thiosulfate. So I find the oxygen mole by divided by 4. So this is 6.325 times 10 to the power negative 6. Okay, now the mistake I made is in 60 centimeter cube of conical flask. That was my mistake. The question now is why is it not 60? Rather, the answer was 30. Because if we check back on top again, the river water is 30. Correct? River water is 30. But I took the whole thing, which is 60. Okay, that was my mistake. Okay, so if 30 centimeter cube is this number of mole, Okay, therefore 1000 centimeter cube will be 2.108 times 10 to the power negative 4. Bear in mind, sodium thiosulfate only reacted with the oxygen in the river. The river mixture is only 30 centimeter cube. The rest of the things like 10, 5, 10, or whatever 5 they add, right? All these things are like the acid, the alkaline iodine thingy, yeah, that one. Okay, now next, or the potassium iodide. Now, freshly distilled water does not contain any dissolved oxygen. Correct. A student decides to run the procedure on a sample to freshly distilled water. Wait, a student decided to run the procedure on a sample of freshly distilled water that does not have oxygen at all, and at the end obtains a value of 2.26 mole per dm cube. So freshly distilled water shouldn't have any dissolved oxygen, but when the student go and do the experiment, he found out there is a very, very minimal of 2.26 times 10 to the power negative 5 for dissolved oxygen. So just why the student did not get a value of 0, assuming the procedure was carried out correctly. So the answer is there was a small amount of oxygen in the other solution. Because remember, distilled water is added over here at the last phase, which is the washing part. So this one, technically, you shouldn't have any oxygen. But when he do the whole experiment, he got a minimal volume. So the answer, I think that what they're trying to say here is the oxygen may be dissolved inside here or perhaps here. All right, that causes some reading to appear. All right, and not the distilled water. It's not the distilled water's fault lah. Okay, so there was a small amount of oxygen in the other solution, but definitely it's not from the 10 centimeter cube of the distilled water. Because when you run the procedure on a sample of freshly distilled water, you also got to add the remaining things like this is the positive control or rather negative control. You still got to put the manganese sulfate, you still got to put the alkaline aqueous potassium iodide, you still got to put the dilute sulfuric acid and water. This is the negative control. Okay, this is the negative control. All right, yeah. So I think it's because of these three, they contains a little bit amount of oxygen. That's why they gave some reading over here. Okay, now suggest how the value 2.26 could be used to improve the answer in F. Because the oxygen 2.26 is found from the three solution that I circle, which is the sulfuric acid, or it could be the aqueous alkaline potassium iodide, or perhaps it was the manganese sulfate. So how can we improve our answer? You gotta subtract. So subtract the 2.108, which is the river oxygen, with this part, because not only the river had oxygen, the remaining three also had some oxygen, which is 2.26. All right. So the oxygen from the remaining three got to be subtracted out. So you have to take 2.108 and subtract it with the 2.26. Okay, so therefore the final one is 1.8. So this is to nullify not the distilled water, rather it is to nullify the remaining three, which is the manganese sulfate, the potassium iodide, and the sulfuric acid. Because your distilled water, DH2O, they already say no oxygen. So that means these three remaining guy has some oxygen, and your river also has some oxygen. So if you want a very accurate value of the river oxygen, you're going to minus these three oxygen. Okay, so you need to do a subtraction. Part H. Suggests why this method is unsuitable for samples of tap water that has been purified by chlorination and so contain chlorine. So my answer is because chlorine will also react with sodium thiosulfate. That is my answer. All right. A lot of times when they say that why is it not suitable when we add things, right? Obviously, the thing that you want to add in will interfere with your reaction. That's the reason why you don't add in. All right. But I went into quite detail. I said that because chlorine will also react with your sodium thiosulfate. So maybe your so-called Biot reading will appear larger than expected. Exactly how they react, we don't know. Perhaps it's a redox. Okay, perhaps it's a redox. So come to think of it, right? If sodium thiosulfate reacts with iodine, that means iodine is reduced to iodide. Correct? So that means if your chlorine is also inside your conical flask, okay, while you're doing titration, your sodium thiosulfate is also reacting with the iodine from the brown color, so it turned pale yellow. So if you have chlorine, so sodium thiosulfate will also react with the chlorine to give you chloride. Correct or not? Okay, that was me lah. Okay, but they say chlorine reacts with the same way as oxygen. Okay, I mean, perhaps I'll get my mark lah because we don't really need to know exactly what happened. All right, so done. Let's go to question number 2. The activation energy EA for the reaction between hydrochloric acid and your aqueous sodium thiosulfate can be determined by an initial rate method. Okay, so I hope you all know what's initial rate method. Initial rate method means we will use the initial rate to represent the whole reaction rate, because we know as time progresses, the rate will always decrease. Okay, the highest rate of reaction will always be at time 0, 1, because that's where your reactant are present in the highest concentration. So when time progresses, the reactant concentration will decrease. That's why your rate will also decrease. So we normally will use the initial rate to represent the whole reaction rate. Is a representation. Okay, so that's initial rate. So we have acid and sodium thiosulfate. You will get your white or off-white or pure yellow PPT. So this is also an experiment in your practical paper. How to detect for thiosulfate ion. This is your qualitative analysis version. So you pour dilute acid into your sodium thiosulfate, you will get your white or off-white or pure yellow PPT. The longer you leave it, the more it becomes on the yellowish end, because sulfur is yellow lah. All right. And of course, remember SO2 is a pollutant, so you don't breathe too much of it. So the solid sulfur is formed as a white suspension in the reaction mixture, and the reactants are mixed at the time T for a fixed quantity of sulfur to be formed. So this is considered as a discontinuous type of measurement, okay, of rates. So there are generally two types of setup when you want to measure rate. I believe you've seen this before in practical paper, where you take the reading of the thermometer every 30 seconds. So that is called continuous measurement. So every 30 seconds, you want to check the temperature reading. So it also can be every 30 seconds, you want to check the pH reading, or every 30 seconds, you want to check the electrical reading. Okay, that is called continuous. This continuous is like this experiment where you record the time for a fixed quantity of sulfur to be formed. So for example, you may want to put this on the weighing balance. All right. You will start the stopwatch when everything is added, and then you stop the timer when you maybe get, the amount of time taken for 1 gram of solid sulfur to be formed on the weighing balance. So you have a destination or an objective for you to achieve. So it is just like the time taken for the blue bag to appear. So you sit down there, then you wait until your blue bag appear, or maybe your blue bag disappear, something like that. So this is called a discontinuous type of setting up of rates. So the measure of initial rate of the reaction is 1/T. So rate is 1/time, but theoretically, rate is defined as the change in concentration over the change in time. But because in practical, right, it's very time consuming for you to go and convert all the numbers to concentration. So rather they just constant the whole thing and give you a 1. Okay. Now, standard solutions of the sodium thiosulfate and the HCl are supplied. Measurements are taken for a series of temperature using the following procedure. Number 1, a thermostatically controlled water bath is set up. Okay, that is to ensure the temperature is constant, because otherwise, if the temperature changes, then the rate will also change accordingly. Number 2, the 100 centimeter cube of conical flask is labeled A, and a second 100 centimeter cube conical flask is B. So you got an A and B, 2 conical flasks now. Now, what happened now is, let's do a drawing. This is called A, and in A, you have the sodium thiosulfate inside here, Na2S2O3. And A is placed in the water bath, okay? So you have a temperature here. A is placed in the water bath to keep him at a particular temperature. And for B is the other conical flask, so perhaps I use a different color. This one is the HCl. Let's put blue, HCl. This is B. So let's say you have another conical flask over here, and they are placed into the same water bath. This is to ensure that the both of them are at the same temperature. So you wait for 10 minutes. I suppose this partner is to ensure that they are equilibrating the reaction temperature with the water bath temperature lah, to ensure that they hit whatever temperature you intended to on the water bath. Okay. Now then step 6, flask A is removed from the water bath and placed on a towel marked with a black cross. So we need to transfer now the flask A. So this is like the top view. You have an X and you're going to put your conical flask here. Okay, that is your flask A. You take it out already from the water bath. And then the contents of flask B are added. So immediately you got to add your HCl in, which is the flask B. So that's where you will start to see the formation of the yellow or a white, off-white or white suspension or pure yellow PPT. And I think you're going to record the time where the so-called black cross disappear over here. Okay, so when the contents of flask B are added to flask A, the timer started and the timer is stopped when the black cross is no longer visible. Time is recorded. Part A, suggest a reason why is it necessary to wait for 10 minutes. I said to allow both solution to equilibrate or to reach the desired temperature by the water bath. So marking scheme says to ensure the solution and the solution A and B are of the same temperature. That is what they say lah, because A and B got to achieve the same temperature, and the temperature is the temperature of your water bath mah, correct? So we don't know what's the temperature that they want lah, okay? So I think for me, I will get my marks because I said to allow both solution to equilibrate to reach the desired temperature of the water bath that you intended to, okay? So part B. The procedure does not mention how a value of the temperature of the mixture during the reaction is obtained. State the temperature measurements that should be taken and at which stage in the procedure they should be taken. So now we don't know what temperature, and they did not tell us at a particular step where we should measure the temperature reading. If you look up here, none of the step here address when the temperature reading should be taken. So it is our question to answer when. Okay, so for me, all right, I said that step 6 after flask A is removed. Okay, because the minute you remove from the water bath and put it on the towel, you should take the thermometer reading. That was me. But the marking scheme, let's go to marking scheme 2B1. Take the temperature of reaction mixture in flask A at the start of the reaction. I said in step 6, the minute you take it out, you take the reading. But for me, right, I wrote that step 6 when you take it out, but that is before adding HCl. But if you look at marking scheme version, they say at the start of the reaction. My question now is, what is at the start? They gave us step 7. So let's look at step 7. Step 7 means the contents flask B are added to flask A. In other words, means for marking scheme perspective, they should take the initial reading or the temperature reading when flask B is added to flask A. But my answer was only flask A only. That was before flask B was added to it. So I don't think I'll get the marks. Okay, so what we are trying to see here is you take the temperature reading when flask B goes into flask A, you start the timer and you take the temperature reading. So it's a lot of handling to do at time 0. Okay, so that's what they mean by at the start, so-called step 7. Okay, or they said step 6 immediately before the reaction. Okay, so maybe this part I can get my marks because they said immediately before the reaction. I took the temperature reading before added HCl. So maybe I have fulfilled this part lah. Okay, before adding HCl. All right. Yeah. So, or they accept immediately after step 5. Let's look back at what is step 5. Immediately after step 5 means after you wait for 10 minutes, all right, you can take the temperature reading already. So I think they are quite lenient to this part. And then the problem here is A and D. You have to fulfill both. At the end of the reaction, step 8, when the cross is no longer visible, which is step 8. So over here, I don't get the marks. I think this part I managed to fulfill. But the problem is I did not write at the end. So you're going to take an initial temperature and final temperature and you do an average of the two. All right, so that's the answer. So part B2, state how to use the temperature measurement to determine an accurate value for the temperature of the mixture during the reaction. Okay, so I said take a before mixing and after timer is stop temperature. So that means before and after and find the average. So they say mean temperature. Okay, so it's quite straightforward. A student carried out the procedure at 3 different temperatures and record the measurements in table 2.1. Complete table 2.1, record values for temperature to the nearest whole number. Normally in practical paper, temperature is to 1 dP, but here, paper 5, they want us to record in whole number. All right, and the values for 1 out of T to 4 decimal place. Okay, so this is a process data. Normally, process data, we will use 3 to 4 significant figures, but here they wanted 4 dP, we got to follow 4 dP. Okay, so let me write down here. You want a 4 decimal place, and this one, you want the temperature to be whole number. Okay, so therefore, I think this one you just check whether did you make any mistake. Now next, a student carry out the procedure at 6 different temperature and analyze their data to give the result in table 2.2. So this is 1 divided by temperature, and this is the log rate. They just log the rate. Okay. Now the reason why they log, actually is no need to, you don't really need to know one, but just in case you want to know why they do a log, is because it's very troublesome to plot the graph, all right, using 0.00574 dp. So if you log this number, it can come out close to an integer, which is very convenient for us to plot number. It is easier to plot a 1.47 rather to go and plot 0.0109. So there's too much of monitoring to do. So the reason why they do a log is because they're trying to make it into an integer for our convenience. All right, just so you know. Now use the results to plot a graph to show the relationship between rate, just so you know this is actually rate. It is rate and temperature. Okay, and use cross to plot each data and draw a line of best fit. Again, a line of best fit can be curved, can be straight line. You see what is best. So I will zoom up to show you all how my line looks like. All right, please ensure that you drag the line as far as possible, okay? Because you never know, sometimes you draw a little bit too short, suddenly you needed to extend your line, then your line is no longer smooth because you have to draw 2 times, even though it's the same line, okay? Now, let's look over here. If you can look at my graph, right, you realize I have something a little, one above the best fit line, about here. I don't consider this anomaly. It's just slightly above, but I don't think it's so far until an anomaly situation. And I also plot one, I saw one below here. So best fit line, maybe you want to look where you have equal number of crosses above and below the best fit line. So I think mine is acceptable, okay, for mine. So maybe you want to just compare, you want to pause the video to see and compare mine and yours, okay? Now then let's look here. Now, determine the gradient of your best fit line and state the coordinates of both points you use in your calculation. These must be selected from your line of best fit and give the gradient to 3 significant figures. When you select coordinate, please select 2 coordinates that is as far as possible lah. So what is the boundary? Try not to choose 2 coordinate that is 50% or lower than the grid. So for example, what you can see here is let me plot for you where are the 2 coordinates I have selected. I think I selected 0.00285 here. I think I should be able to track back. Just give me a moment. 0.0285. Okay. I should have make it a bit more obvious. Negative 0.8. Okay, I think I took this. Yeah. This is one coordinate that I've taken. I chose. And the other one is the negative 2.54. I think I checked y-axis. Negative 2.54. I think mine is here. 2.54. Now, it's because I dragged my line very far. Okay. So I selected the furthest two. So what I meant by recommended boundaries is I chose these two because so happen the coordinate falls on the grid properly, not in the middle of the grid. So I chose these two. But for you all, or I don't know what you all do, but for example, what are the situations that I will not recommend? The situation that I would not recommend are situations like this. For example, if let's say you take one here and the other one is here. Now, I think this is a bit too short. So therefore, how short is short? All right. I wouldn't recommend if you're even for here, like this. I wouldn't even recommend that because you can see that I only cover less than half of the grid. So if you take the y-axis and x-axis, right? So let's just look at the y-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 boxes, right? 9 boxes. Therefore, if you take these two, you only cover 1, 2, 3, 4, 5. Okay, then can 5 boxes around there. Yeah, you cover half of the y-axis grid. To me, I think it's okay lah. I will not go lesser than 50% of the y-axis. I wouldn't do that lah. For example, if let's say we go back to the original one, which is these two, this one you don't even hit one box what more half of the 9 boxes on the y-axis. So when you want to choose two coordinate, I would suggest you to choose more than 50% of the y-axis grid or the x-axis grid. So that is what I'm trying to advice over here. Okay. Now, your gradient and my gradient shouldn't be too far off, everybody. All right. So I calculated a gradient to negative 2.32 times 10 to the power of positive 3. The reason why your gradient and my gradient shouldn't be too far off is because we use the same data provided by the examiner. So if your gradient is a little bit too far off than mine, it means that the way you draw your straight line, it's very different from my straight line. All right. Maybe your one is more steep than mine, or maybe your one is less steep than mine. All right. But you shouldn't be too far than the negative 2.32. All right. Now, next. An equation relating time and temperature variable is shown. So this one is very common in paper 5. Normally, they will use y equals to mx plus c, which is a straight line formula. All right. So you need to go and observe clearly. Now, your y-axis is your rate. So you look at your y-axis, y-axis over here. Can you see this is y-axis? Log 1 over t. Your x-axis is 1 out of temperature. So if you go over here, this is the y. This is the x. This is your c, which is the y-intercept. Okay, which is y-intercept, but do we even have y-intercept here? No, we don't have a y-intercept. It's because we are only 0.0028. So we don't have enough data to look at y-intercept. Okay, and then your gradient, obviously, is the one that I have circled here. The remaining thing here is your gradient. Okay, so determine the activation energy of this reaction using this equation and your answer to D2. So therefore, your gradient is minus 2.32. Take your gradient and equate it to the function, which is negative 0.434 EA divided by 8.31. Now, everybody be very careful. R. The R over here, I need you to go to your question paper, last 2 pages to check what is the R. Okay, you have to follow your exam series R. So for me, the exam series is 8.31. Therefore, I put 8.31. Please check. Sometimes 8.31, sometimes 8.314. I don't know your one is which version. Please go according to your question paper series. All right. So my one is 8.31 according to my table of specification. So I put 8.31. So therefore, there you can calculate what is your EA. Now, when I calculate out, right, okay, I realized that I need to derive the units. Okay, I need to derive the units. So therefore, I need to go and find out what is the unit first. So first, I have the 0.434 EA divided by the 8.31. So when I go and find the units of 8.31, right, it's actually joule per Kelvin per mole. Okay, and then after that, the temperature here is Kelvin, right? So this Kelvin and this Kelvin can cut, right? Okay, so therefore, when I shift the whole thing remaining here, I get joule per mole. Yeah, so whatever you calculate the number, 44422, right, is actually joule per mole. Okay, now marking scheme answered in kilojoule per mole, but joule per mole should be accepted if values are correct, because when I cut the unit off, All right. The remaining one over here was joule per mole, which is why I answered joule per mole. But if you check marking scheme, you will see it is kilojoule per mole. Nothing wrong so long you tally according to it. Okay, so for those who want kilojoule per mole, not a problem. You need to divide this number by 1000. So the other version is 44.422 kilojoule per mole. Doable. This is also acceptable. Okay, but because I never divide by 1000, so I just remaining as joule. Now next, use your graph to state whether the results from the experiment are reliable and justify your answer. Okay, now, so let me look at this thing. Use your graph. So if I look at my graph, okay, for me, I answered the results are reliable, okay, as most points falls on the best fit line, or no anomalous point was found. So therefore, I think my results are reliable. So can we look at marking scheme? Is there any other alternative over here? So they say that, yes, my results are reliable. There are no or there are few anomalous points, or most points lies on the best fit line. Or you also can answer no, my results are not reliable. There is an anomalous point, or some of the points do not lie near the best fit line. It really depends on how you think, but you have to give an explanation now. All right, now next. Suggest a change to one controlled variable that the student could make so that the time measured for a given temperature is shorter. Okay. One controlled variable. So if you want to measure the time given for a particular temperature is shorter, that means you want it to be faster lah, so that the time is shorter. So if you want to make it faster, you got to increase the concentration for one or both, because you cannot change the temperature anymore, because in this experiment you're changing the temperature. You cannot change the temperature anymore. So you got to figure out, is there any other ways that we can still increase the rate without touching the temperature, because they said for a given temperature. So answer is increase concentration for one or perhaps both the reactant. All right. So therefore, I think we are done with all the questions here.